What is it? Okay, so I just want to, we did this problem, which was a two-body problem. And when we're doing these two-body problems, we just treat each block separately, and we go through all 4 steps for each of them. That is, we draw all the vectors, we draw the vector diagram. That's where we draw the vectors on a coordinate system, where we select our coordinate system, we figure out the angles, and then we resolve the vectors, and then we apply Newton's second law. All right, where we say the sum of the forces in either the x or the y direction is equal to the mass times the acceleration. And one thing that I did here was I said that the forces acting on this block were like this, that I had this Ft1, which was this tension, and then Ft2, which was this tension right here. All right. If you think about this, I have this, if I just look at this point on the rope, I have this force that comes down, right? And so there's going to be an equal but opposite force that's going in this direction. And then this vector, the blue one that I just drew here, is going to be the equivalent of the sum of these two vectors. All right, because it's equal and opposite this black vector. All right, so that's how I can go about saying that I have these vectors, these forces, acting on this block. You with me on that sort of kind of? All right, let's do some problems. Actually, let me see what else we have here. We might have a few more things. Okay, why don't y'all try this one right quick. Just a little bit. It just says that a dock worker loads a ship on a crate, a 100-kilogram crate. To know what is the difference between kinetic and static friction. How do you calculate them? About 15 more seconds, Joe. Stop at 140. Let's see, is A right? A is right. So here you want to determine what is the force due to kinetic friction. I have this object, I push on it, and it requires 400 to get it going. So if that's going to be my static frictional force. That's that initial big force to require it to get it in motion. But thereafter, it's only 300 newtons, right? So this is going to be my Fk, which is equal to mu k times my normal force. I have a 100-kilogram crate. That means the weight of that crate is 1,000 newtons, or 980 newtons, if you will. And since it's on a horizontal surface, the normal force is equal to the weight. So I can solve for mu k is Fk over the normal force, which is 300 over 1,000, which is 0.3. All right. Static frictional force is when it's not moving. Kinetic is when it is moving. Good job. We're going to skip this. What happens to the frictional force here if I increase the angle of this? If I make this block go up, what happens to the frictional force? First of all, what is the frictional force dependent upon? Two things, right? The what and the what? The normal force and the coefficient of friction. So what happens to the normal force of this block as it lifts up? Does it increase, decrease, or stay the same? What happens to the normal force if it goes all the way vertical? Okay, what? It zeroes out, right? It goes away completely. So as you increase the angle, what happens to the normal force? It decreases, right? So the normal force decreases, and so the static friction will also decrease. This normal force is equal to the y component of the weight. That's Fw sine of phi. Fw sine of phi, where this is our angle phi. Remember when you're working with these inclined planes, which you will likely see an inclined plane. We might have some other variations, but likely see an inclined plane. You have to take, if you're doing the cosine sines like we normally do, you have to find the angle with respect to the x-axis, meaning if you use the cosine for the x and the sine for the y. So this is equal to my normal force, and as that angle increases, or excuse me, as theta increases, phi decreases, and so the normal force also decreases. Or you can just think of the extreme where it goes all the way up, then the normal force goes away completely because it's not even touching the surface anymore. All right. Let's try this example. I'm going to sort of rush through it. We've sort of done one similar to this before, but I want to get into some two-body problems. Andrew?
Question. Would it be harder to push up if you increase the angle?
Would it be what?
Harder to push the block up if you increase the angle?
Right. So if you increase the angle, what's going to happen to the block? At some point, the component of the weight that goes down the inclined plane. What happens if you pull it up eventually to the block?
It'll start falling.
Right, it'll start sliding down, and that's because this component of the weight, this is Fw cosine of phi. This component of the weight, as phi decreases, will increase. So that, it's going to increase because when it goes all the way up, that component of the weight is equal to the total weight. Right now, once it increases so much that it exceeds the maximum static frictional force, then it's going to start sliding. Does that answer your question? The answer is yes. It is harder to keep it up because more of the weight is directed down the plane of the incline. Right. So it's going to start sliding eventually. And then static friction will apply in order to be kinetic friction. All right. All right, let's look at this. I want to know what is the minimum static frictional force, or what is the minimum mu, so that this block doesn't move. Let's see, did I give an angle here? I'll need an angle. We'll just say 30 degrees. So we'll say that theta is equal to 30 degrees. Now, I've already labeled all the forces here. And so that's going to be step one, just where the force is labeled. You can go ahead and do a vector diagram, and I'll do that here, although it's sort of already done. But I'll draw my vector diagram. I have my normal force pointed straight up, my static frictional force in that direction, and then my weight. And I want to know this angle. That angle is 60 degrees. And then what's the step three, the next step? Step one is label all your forces. Step two is draw your vector diagram. Resolve your vectors. So in step three, I resolve my vector. Again, steps 1 and 2 can be combined, but while you're practicing, I find it useful to do them all. My normal force and my static frictional force are there. And then I have Fw sine of 60 and FW cosine of 60. All right. Step 1, step 2, step 3, and now step 4 is to do what? Apply Newton's second law. So I say the sum of the forces in the x direction equals max, and the sum of the forces in the y direction equals may. You're going to go through all these steps regardless of what I'm asking for. And once you get to this point, then you'll write your system of equations, and then you'll say, okay, what am I looking for? And in this case, we're going to be looking for mu. I have a third equation here as well, which I'll just write over here to the side, and that is that Fs is equal to, or is greater than or equal to, mu s normal force. Okay? So in both of these cases, the acceleration equals 0. This is a static problem, so I can say the sum of the forces in the x is Fw cosine 60 minus Fs is equal to 0. And then over here I can say Fn minus I'm looking for mu. So what is going to be my plan here to find mu? I can find Fn first, right? And I can use this y equation here to find Fn. You know, that'll give me part of what I need to find mu, because that'll give me my normal force. What else do I need to find? Right, I can find my static frictional force, which I can find it here, my static frictional force, and then that's the end of the problem. So first I find Fs, or Fn, it's Fw cosine of 60. So Fw is, what was it, 10 kilograms? Yeah, 10 kilograms. So that's going to be 10 times 10, I'll say 100 newtons, times 0.5, which is equal to 50 newtons. And then I find my Fn, which is going to equal Fw sine of 60. So that's 100 newtons, sine 60, 0.86, yeah, 0.86. So it's going to be 86 newtons. And then I can put those two together, and I say that mu equals Fs over Fn, which is 50 over 86. I get 0.6. All right?
When we're figuring out these problems and on the test and stuff like that, if we use 10 for gravity, it's not
10 is fine. Yeah, I'm not, yeah, that's fine. 10 is good. I recommend that. To use d equal 10 makes it a little easier. Alright. Y'all are okay with this sort, right? Okay with these types? Yeah? Okay, let's do some more practice. Let's see what else we have here. I'm going to skip the quick test. I really want to get onto these problems because these will help prepare you more. Alright, so here I have two blocks, and they are on an inclined plane. The masses are given, and I give you the coefficient of friction between block 2 and the plane. First thing I want you to do is draw all the vectors on the block. So on M1, I want you to draw all the forces that are acting on M1, and then draw all the forces that are acting on M2. And I also tell you here the direction of the acceleration, which is up the plane. How many forces on M1? 2. There are 2. That one's simple, right? There are only 2 forces acting on it. I have the force weight. And listen, guys, when you're drawing these, you need to be very careful that you keep them separate. So we're going to have a lot of force weight and a lot of masses. So anytime you're writing the force weight or the mass, make sure you put a subscript for the proper block. Go ahead and draw your forces for block 2 as well. We're just doing step 1 at this point. What are the forces on block 2? Okay. The tension of the weight, not Fs, but Fk, the kinetic friction. They'll say normal force? Yeah, normal force. So I have the normal force. Remember, the normal force is always perpendicular to the surface. Ft. Anytime you have a tension in a rope, that tension is felt all throughout the rope. So our two tensions here are going to be exactly the same. So I don't need to differentiate in any way. Be very careful with my force weight that I label it as Fw2. And you can even do different colors like this to keep them separate. And then I have one more. What is it? And what's the direction of it? It's opposite. Remember, with our friction, it's always opposite the direction of motion, right? So if I push on this desk, there's a force retarding my motion that's in the opposite direction. And here my acceleration is up the plane, so my kinetic friction is down the plane. So friction always opposes the motion, and so my Fk is in this direction. All right, so there's my step 1. I'm going to skip step 2 and just do it right here. So I'm going to draw, that's my y-axis. This is my x-axis. And now I just want to label this value. What is that angle right there? 60. That angle is 60 degrees. All right, over here, I just have x. All my vectors are on the y-axis, so those are fairly simple. So those are my vector diagrams too. All right. You would definitely want to do this step because it helps you to visualize all the vectors. You can think about what vectors are there. And plus, if you make a mistake later on, it helps me to see what you've done, and then I can give you credit for what you've done correctly. Okay, so please do this step. All right, now our next step is to resolve the vectors. And then we'll do the fourth step, and then we'll address the questions. So I'll do this up here. We're just going to resolve them for this one. Fn, Ft, Fk. The x component is what? Cosine 60. Good. And here I have Fw2 sine of 60. So now I've resolved the vectors. And now I want to write my equations. And I'm going to have 3 equations for these 2 vector diagrams. The sum of the forces in the x and the y directions here, and then just the sum of the forces in the y direction here. And then I can address the questions that I have. Oh, and then I'll have a 4th equation too, and that'll just be the kinetic friction is mu k times Fn. All right, I'll just take a moment. Go ahead and write out those 3 equations for Newton's second law. The sum of the forces in the x direction, the sum of the forces in the y direction for mass block 2, and then the same for mass block 1. Not forgetting, of course, this is a dynamic problem. So normally where we have MA, we've been setting it equal to 0. That's not the case here. It's not 0. As it's set up, how is the acceleration of the block 1 compared to the acceleration of block 2? Is it bigger, smaller, or the same as?
It's what?
It's the same, right. So anytime this block moves down a certain distance, this block is going to move up the inclined plane the same amount of distance. All right. So you should already have your equations. I'll write them here. Sum of the forces in the x for block 2 is Fk minus Fw2 cosine 60, or excuse me, plus minus Ft equals M2A. Big sticking point, a big problem that people make is they don't label this mass, and then they get their masses confused. But for each of them, you need to make sure you keep their mass distinct, and that you know what is the mass of the block. Sum of the forces in the y, should already have it written, from mass block 2, Fn minus Fw2 sine of 60. That's equal to M, what's it equal to? Sum of the forces in the y is 0, right? It's not moving in the y direction, and so this is equal to M2AY, which is equal to 0, because AY equals 0. And then I have the sum of the forces in the y direction for block 1. It's going to be Ft minus Fw1 equals M1A. All right. I can also write another equation. We'll just write it here. It's Fk is equal to mu k times Fn. All right, so I have 4 equations. So I go through and label all my unknowns. Well, it's not necessary. We'll just follow this. So I sort of make it a little easier here because I lay out the questions here. What is the normal force acting on block 2? Which of these can we use to find the normal force? Right, that second equation. Notice here that there are no unknowns except for the normal force, because I know what Fw2 is, and I know the mass, so I can find that. So for part A, I'll say Fn equals Fw2 sine of 60. So this is where we'll look at our masses. Our mass 2 is 1/2 kilogram, so 0.5 kilograms. .44. Oh no, what did I do something wrong? Oh, times 10. Right, 4.4. I'm sorry. Times.
It's actually 4.33 if you do it.
I didn't put in my G there, so it's 4.3. You're right, or 4.4. 4.35.
4.33. So I
Okay. I'm gonna leave it at 4.4. It depends how you round. You can get different numbers. All right. So that's part A. Now I want to know part B. What is the frictional force? All right. How am I going to find the frictional force?
UK times FX.
Right. So I already have mu. So if I want to find my frictional force, I just say Fk equals mu k times Fn.
How did you do
Mu is given, right?
Oh,
yeah, it's
I
given
see.
up here.
I'm sorry.
That's okay. 0.4 times 4.4. It's 1.8 newtons. All right, and then what is the acceleration? I'll give y'all a minute. Y'all try to find the acceleration. So I'm going to look at these system of 4 equations and figure out how in the heck can I find the acceleration. By the way, guys, if you write these equations out correctly, that'll be a good portion of the credit. So even if you don't solve them correctly, I'll give you a good portion of it if you just write them correctly. Somebody got a tack for me? What to do here?
You gotta combine the equations because you have two unknowns.
I have two unknowns in each equation. I don't know the acceleration here or here, and I don't know the tension here or here. So there's really no other way than to solve the system of equations. Like, you will have to solve a system of equations, you can bet on that. So I can combine both of these. This equation, I'm going to rewrite it just with the numbers that we know. That's 1.8. FW2 is 5 newtons. That's just m times g times cosine of 60 for 0.5 minus ft equals 0.5a. Is that 1.8, 3.8? So I'll call this equation 1. And then here, solve that equation. My normal force is 4.4. Oh wait, no, not that equation, I'm sorry. We're working here. So it's going to be Ft minus Fw1, 21 newtons, equals 2.1 times A. I'll give you all a minute, try to solve those two. You want to solve one of them, you guess, is that what you said? No. You want to solve one of them for one of the variables, plug it back into the other one, and then solve for that variable. So please practice it. It's good practice for you for now. Call this equation 2. I'm going to go ahead and start solving it. You might have chosen to do it a little bit differently than I have, but it's going to work out the same. what y'all got? 7.6 newtons and negative 6.4 meters per second squared. What I've done here, and you might have done it a little differently, you could have solved a different equation, is I took this equation and solved it for ft, and then I plugged that in to ft here. And right here, see I said 4.3 minus 0.5a minus 21 equals 2.1a, and then I solved that for the acceleration. All right, and then over here, I plugged that acceleration back into this function for ft and solve for ft.
But the question, C was the one that was the acceleration of block 2, right? So block 2 would be negative.
Yeah, they're both going to be negative.
That was
Negative 6.4.
And that's the answer for C.
That's the answer for C. Yeah. Yeah, so I could have stopped there. I didn't ask for ft. Is that what you're saying?
Yeah, I just
why not, right? It's a little bit good more is better. Is that right?
Yeah. So do a little extra, that's 30 points extra coverage.
Yeah, right. Okay. I'll have this posted online, guys. I'm sorry. I forgot to record the sound last time, but I'll have it online if you want to look at it. And there's
just negative 6.4.
the acceleration of block 2 is negative 6.4. And remember, the block is accelerating in this direction, but this block is also accelerating in that direction. They have the same acceleration because they're attached by this unstretchable cord.
Which, can you go down again? Which equation did you use to fill in? So you took it.
To fill in what? Is that clear? Just a second. Yeah, and
Block 2 acceleration be positive since it's going up the y-axis.
it's not going up though, right? Because the way we draw our coordinate system. Rob, can I move? Are you, You okay?
And block 1's going down.
No, they're both going in the negative direction. I know it looks like it's going up in the y direction, but the way we drew our coordinate system, it's going in the negative x direction. You see, this is our x-axis, and it's moving in this direction to the left. It's not moving up, it's moving to the left. Because we rotate our coordinate system. If you did rotate the coordinate system, it'd be a lot more complicated, because it would not be moving on the x-axis, it would be moving sort of at an angle. Makes it a lot more complicated. Somebody else had a question. Did you say that?
See, you put it back down.
Okay, yeah.
But I got it there.
Okay, you got it? All right. Let's see what we got here. Is this a homework problem?
Yes. Yeah, it's okay.
That's the end? Don't want to work through some more practice problems? All right, let's look at some old exams. These are exams that are not on the where they don't have video solutions. So I want to do this one. You're not going to see a one-body problem. Well, you could. Like I might have an additional simple one-body problem. This one's not terribly complicated. But this one has a spring. You had a homework problem that had a spring in it. And so you might want to write this down. You have some blank pages at the end. If I have an object that's hanging from a spring, then there are two forces acting on this object. There is the weight of the object, and then there is the force due to the spring. And we can find that force. It's equal to the magnitude of the force is equal to k times x. This is called Hooke's law. We'll have a lab on this later. And we'll actually get into oscillations quite a bit in a later chapter. Right now, you just want to focus on the force due to a spring. If you take a spring and you stretch it, the more you stretch it, the greater the force is, right? It's true. Like if you stretch it more and more, then the force gets bigger and bigger. And this is a linear relationship. So as you increase x by a certain amount, you increase f by that same factor. So if you double x, you double f. And this is proportional by what we call Hooke's constant, or the spring constant, which is k. This is just measured experimentally, and it's a value that's given to you. So that's what we have here, is we have an object hanging on a spring, but it's in an elevator, so it's moving upwards at a certain acceleration. I want to find how much does it stretch. So I want to know what is x equal to. Your first step is just going to be draw your vectors. So sketch out your picture and draw your vectors. How many forces on this one? There are only two, right. There's the weight and then the force due to the spring. Don't have to resolve vectors here, so jump on to step 3, or step 4 rather. Where you apply Newton's second law.
Would you have
You could potentially see a problem like this, but I would expect you to be able to do it pretty quickly. Did I get the same answer as you?
would you get 10 meters per second?
Oh, that's G. Instead of 9.8, I just used 10. Remember, guys, on my test, show your work, because I will, even if you get the wrong answer, I'll still give you credit if you portion of your credit line.
I smelled smoke and smelled my.
No, it's it comes from outside.
And it's just,
They're burning. Are they burning pain this time of year?
no, they shouldn't be.
Burning something.
It's actually supposed to be. It's actually illegal. You can't burn cane because whenever you burn it, it creates so much smoke it'll block roads. That's why in November they burn around November, and whenever they burn it down to Maya, they have to literally close off down the Maya because so much smoke you can't see 3 feet in front of your face or even in front of your car.
All right, guys, y'all got this okay? I should be okay with this, right? Yeah.
Just do the math there.
Okay. Well, if you have calculation errors, I usually just count off a point on the quizzes. So, can I take this away? I'll just solve for FS right here, and then plug it back into Hooke's law to find. Yeah, Joseph.
Can you do like the last time tell us like what numbers to go up to on the OE games?
Yeah, I'll send that out to you on email. Okay. Yeah.
So it's pretty much saying that 1,200 that's K.
I'm sorry, what?
You're pretty much saying right there that 1,000 is K.
Right, 1,200 is given in the problem. Where is it?
Yeah, right there. That's what I'm saying.
Yeah, the spring constant, 1,200.
Okay.
All right. If you have to do a spring problem, I'll give you Hooke's law. Don't worry about trying to memorize it. In fact, there are really only 2 equations that you need to know.
No, I was just
Yeah,
we
so-
just had spring constant.
Yeah. the three equations you need. The two kinematics equations for projectile motion and the F equals mx. So there's really not many equations to know. It's just really on how to use them. Did y'all hear about that mushroom that passed away? The mushroom, he died. Y'all hear about that? It's really a shame, because he was just, I don't know, he was just a fun guy. Somebody told me that. Who told me that? Was somebody in this guy?
It was a mushroom walked into a bar, he asked for a drink, and the bartender said, "We don't serve mushrooms." The mushroom says, "Why? I'm a fun guy."
Oh, okay. Yeah, well, that's beautiful. What do y'all like there, the bar or the bar? The bar.
Because it's not like, oh, he died.
Maybe that's too much of a downer. Alright, I'll try to get it right next time. Alright, let's do it. I think we have time. Do we? Yeah, it's good. Oh. Oh boy. Okay, so here, this is follow 7. The previous one was follow 9. All right, and I will send y'all an email out for all the exams. But we're looking at projectile motion, we're looking at vectors, and we're looking at Newton's laws. So if you see anything about work or energy, you've gone too far. But I'll send an email out. All right, so here I don't give you the picture, but let me draw the picture for you. And we're running a little short on time, so I'm going to just work through it. I have blocks A and B. They are 3.7 and 8 newtons, and they look like this. This is A, this is B, this is 3.7 newtons, and this is 8 newtons. And they're coming up a 20-degree incline.
How does this string massless?
The string? But it has negligible mass. So the mass of the string is a lot less than the mass of the block.
It's
so
a line of electrons.
that wouldn't be massless either, would it? And I want to know the coefficient of friction for A is 0.1, and the coefficient of friction for B is 0.2. So presumably block A and B are made out of different materials, so they experience different friction. Like one's wood, one's rubber, or something like that. All right, and I want to know the acceleration of the blocks. That's it. So there are no forces acting on it other than the normal force and the weight and the frictional forces. So I'm going to draw the forces on each of these. So for both of them, I have weight, FWA, FWB. For both of them, I have a normal force, FNA, FNB. And then for both of them, I have frictional forces, FKA and FKB. I know they're moving down the plane because, well, there's nothing pulling them up, right? There are no other forces pulling them up the plane. So,
So FT is
what's that?
FT is the tension.
Oh, yes. Yeah, we can do the tension. Actually, yeah, we'll need the tension. Let me write that. So we have FT here and FT here. All right, and they're both the same. I'll go ahead and draw the vector diagram here and here. So this angle will be 80 degrees, and then you can do a similar one for B, but I won't do that here, just make it too messy. Now we'll resolve my vectors. So for block A, it's going to look like this. FNA, FKA, FT,
70.
Yes, you're right, 70. Sorry about that. Yeah, so the 80 should all be 70. All right, and then for block B, it's going to look similar. This is actually not a terribly difficult problem. Once you get it visualized and you know what it's like. I don't think we're going to have to solve a system of equations. Let's just see. Yeah, we will. Yeah. So I have FNB. Notice that the tension now is the opposite direction because I have one tension pulling down on this block, and then this block the tension is pulling up. All right. Now we're going to write our equations. I'm going to write them, and I'll go and put in the numbers that we know already. I'll start with A. I'm going to write them up here because I can't go down anymore the way I have it set up. So for block A, I'll have these equations. I'll have FNA minus FWB, which is 8 newtons. Wait, is that right? Did I do this correctly? No, 3.7 newtons. FNA minus, oh, I made a mistake here. I'm sorry. Right here, this should say A. Be very careful. I mean, I do this all the time. Just make sure you get your A's and your B's correct, okay, for your masses. So FNA minus FWA. FWA is 3.7 newtons. Sine of 70. That's equal to 0. It's equal to 0 because it's not moving in the y direction. And then FT, which I don't know, plus 3.7 sine of 70 minus FKA, which I don't know, equals the mass of block A times the acceleration. So those are two equations. Let me write the second set of equations, and then we'll go. I'll leave this for you to solve on your own. For block B, looks like this. I have FNB minus 8 newtons, that's FWB, sine of 70. That's equal to 0. And then I have FWB cosine of 70 minus FT minus FKB equals MBA. All right, I'll post this online, but so let me just write out in words what you do next. So for your next steps, and you should try this on your own. So if you get to this part, that's going to be, I mean, if this was a 30-point problem, so if you got to this part, that would be.
Is it 3.7 times 9.8?
No, I give the weight, not the mass. So see, it's 3.7 newtons. It's the weight. Yeah. Be careful. So if you got up to this point, if this 30-point question, I'd probably give you maybe up to 25 if you got it all correct up to this point. Right, the algebra, I'm not too concerned with it. I might, and then if you attempted the algebra and got it wrong, I'm just kind of a couple points off. If you're doing it sort of correct by the right steps. So this is like the bulk of your credit. Rob, do you have a question?
Yeah, so mass 1 is 3.7 and mass 2 is 8.
Right, block A is 3.7 and block B is 8. 3.78. The lighter block is leading right here. All right, and then so find the normal force for both. Find the normal force for both. See here, I can find FNA and FNB simply. Find FK for both. Right, because I know FK equals mu times the normal force, and mu is given for both here and here. So find FK for both. And then you're going to solve this equation and this equation. So you're going to solve the system of equations. Just like we did before, where you solve one for one variable, plug it into the second one, and then solve it for that second variable. All right? This is a fairly complex problem with a lot of different vectors involved. Likely yours would be a little simpler, just to make the algebra simpler. Okay.
If I would have read that problem with it sloping down, right, the way I would have read that is the lighter block leading, how to put the 3.7 leading block.
I understand, yeah. Might affect the answer. I understand. I'll have a figure to explain it. Okay, don't worry about it. And if you have any questions on that during the exam, then I'll just ask
And
you.
it might not make a difference. But,
I don't know if it makes a difference or not, because it switches around your attention point. I don't know, it might not.
I'll just,
Okay.
what made you, guess my question, what made you put it to the left? Other than you just know the,
I don't know. I might have done it the other way. I might have. All right. Y'all have a good day, okay, guys? Guys, wait, hold on just a sec. I'm going to be out this afternoon, okay? Sorry. But if you have questions, come see me more.
Shouldn't be running.